Hi, this is Dustin Ingram. This is my project for the Advanced Artificial Intelligence course at Drexel University Department of Computer Science for the winter 2012-2013 term. My project is detecting asteroids with neural networks. So first, I'm going to go over an outline of what I hope to talk about. First, what's the goal? What's the data and where's it coming from? How did I get started with this data set? How we built the feature set for the data, how I built the neural network, training the network, and eventually the results for the network. So here the goal is to build and train a neural network to correctly identify asteroids in astrophotography data. So how do we do this? Well, here's some motivation from the movie Armageddon, which has so many scientific inaccuracies that NASA actually uses it as training data for potential managers.
STI, this is Flight Director. I want to get that Hubble moving, and I want it now. Roger that. We're moving to Hubble.
It's enormous.
This is the anomaly at 1643. Here's the anomaly at 1658. And here is the anomaly at 1700.
Enough with this anomaly horseshit. What is this thing?
It's an asteroid, sir.
How big are we talking?
Sir, our best estimate is 97.6 billion.
It's the size of Texas, Mr. President.
Yes, sir.
Dan, we didn't see this thing coming?
Well, our object collision budget's $1 million. That allows us to track about 3% of the sky. And begging your pardon, sir, but it's a big-ass sky.
And the ones this morning?
Those are nothing. They're the size of basketballs and Volkswagens, things like that.
Is this going to hit us?
We're efforting that as we speak, sir.
What kind of damage are we?
Damage? Total, sir. It's what we call a global killer. The end of mankind. Doesn't matter where it hits. Nothing would survive, not even bacteria.
My God. What do we do?
Alright, so here's how we really do it. The data set comes from the Sloan Digital Sky Survey, and this is called one of the most ambitious and influential surveys in the history of astronomy. Basically, they use multiple telescopes to scan approximately 35% of the sky, and it's the largest uniform survey of the sky that's been accomplished yet. The data is freely available online for anyone to use in a really easy format. It's basically hundreds of thousands of approximately 900 by 600 pixel images. Here's an example of one of the images. In this image, there is one single asteroid. Can you find it? Here it is, right here in the top right-hand corner, circled in this green box. So, how do we know this is an asteroid? Here it is at actual pixel value. This is what one-to-one representation of this image. Here it is blown up a little bit larger. The question is, how do we know this is an asteroid? How does this work? So, determining and being able to say that this is an asteroid exploits the property of charge-coupled devices, CCDs, which are used as the receivers for the photons in the telescope. The Sloan Digital Sky Survey telescopes use 5 different filters on their CCDs, and they don't operate simultaneously. They basically capture photons in series, and so therefore moving objects across the field of view of a telescope are going to appear in different locations for each exposure. So, for example, Sloan Digital Sky Survey has 5 different filters. 2 of these are visible light, so an object moving might appear in 2 different frames. We know that Sloan Digital Sky Survey always uses the filters in the same order, so the pattern of a moving object is basically going to be represented by a couple spots of different colors. So we look back at our example asteroid, and what do we see? We have a large splotch of yellow, some intermediate value, and a large splotch of blue. And this basically tells us that this is a moving object. The yellow followed by the red followed by the blue is what indicates this. So to get started, we had to build some initial training data because we can't use a non-existent neural network to build training data for the non-existent neural network. So I wrote a small tool to extract potential candidates from the full-scale images. And this is an extremely naive approach. The algorithm is not very good. It produces approximately 100 false positives for every 5 actual positive that it finds. But it's rather conservative. It has very low false negatives. So for every 1,000 images, approximately one of them is a false negative. It is, however, incredibly slow, so this is doing a complex scan of maybe 100,000 possible potential asteroids, and then what we have to do is a manual classification. So of all of the results that it returns, basically I have to sit there and look and visually inspect is one an asteroid or not. And what this eventually yielded was about 250 valid asteroid images, including the one you just saw, and about 500 invalid ones. And this is what we're going to use for the training data. So the next step for our neural network is to build a feature set. And this is probably the most important part of building this neural network, because the feature set sort of defines the quality of how we can interpret the data. So we want to be able to come up with features that are really representative of whether it is positive or negative, or affirmative or negative result. And I came up with a lot of different ones of varying degrees of usefulness. The three I sort of settled on for this project were as follows, and I'll go into more detail of these in the next slides. One was the ratio of valid hues to non-valid hues. One was the best possible cluster collinearity, and one was the best possible average cluster distance. So the first feature is the ratio of valid hues to non-valid hues. And the goal here is to match colors within the image, also known as hues. Basically, the RGB, the red, green, and the blue values are kind of useless to us here. They don't really tell us a whole lot about the image. It's more useful for us to convert these RGB values into the HSV, the hue saturation value space. And what we basically do is filter out pixels in the image that don't match that fall within a valid color spectrum. So anything that's too dark or too light, we're going to just discard it. Anything that's very close to black or white is just not part of our training data. And then we look at and see how many of all of these valid value points fall within 2 standard deviations from an optimal value. So we determine that for an asteroid there are 2 optimal values, and we try to see how many of these fall within 2 standard deviations from what I determined based on the training data to be the average optimal value for each of these 2 colors. And then what's the ratio of this to all the other points that fall within the valid spectrum but aren't a valid hue. So here's a sample plot of the HSV space, and it's sorted by hue value. So we see that we basically have 2 distinct, really good separation between hues. We have one that's one color and one that's the other color, pretty distant from each other. And repeating this over all the training data, we can find the best average for both of these. And then we also see something else interesting here. We're not so much concerned with the saturation, which is the red points, but the yellow points, the values sort of show a peak right at the center of these sections of hue values, and this corresponds to basically the center of the image. So we see a really high value image, and we can see also that values are being any values are being cut off that are lower than 0.25 or greater than 0.75 for this example. And this is again just to limit the very bright and very dark images because they're not as accurate with regards to the hues. So the next feature we attempt to use for our neural network is the best possible cluster collinearity. And what this requires is as another step in processing the data, we use a k-means clustering to, based on the valid hues from the previous feature, to cluster the data points into a couple groups. So basically how k-means works is we attempt to cluster all the points into k groups. Here we're going to use 3 because we're trying to test collinearity, which is, here we use 3, and this produces 3 centroids in the image. So again, here's our example asteroid. We sort of see it, if we were to cluster this based on the hue value, where the points would fall, and then here's the actual result. We sort of see that the blue, the intermediate reddish color, and the yellow are all clustered into groups, and the centers are pretty well balanced between them. So this feature is basically to find the collinearity between the centers of these clusters. So collinearity is the property that a set of points all lie on the same line. So the better the collinearity is, the more accurate these groups are into being an asteroid. So we iterate the k-means clustering a couple of times, maybe about 20 times, to find the best, the lowest possible collinearity of clustering of these groups. And then we use this metric as a ratio between the actual collinearity and the maximum potential collinearity. And we use this formula, given 3 points A, B, and C, to find this value. So this reduces the result. So if the 3 points are directly on lines with each other, the result will be 0, and if they're high, they'll be the maximum value. So again, here's our example asteroid. And then here's the clustering again, and we can see that the centers of these centroids fall basically within the same line, so we should assume that the collinearity is going to be pretty low value for these points. Here's another example of a non-asteroid. This is some other body that sort of has a tinge of the blue and yellow that we're going to kind of be looking for, but it's not an asteroid. It's a little too bright, it's a little too round. They're not the same, not very well balanced between the two colors. And then here's the k-means clustering on the same asteroid. We sort of see that since we're removing the very low value and high value pixels, we sort of have a donut effect going on here. And this is good for us because what this shows us is really bad collinearity here. We don't see a continuous path of one color, then another color, then another color. We see sort of like it's distributed around a single point. So the next feature that we're going to look at is the best possible average cluster distance. This uses the same k-means clusters that we used in the previous feature, but here we're trying to determine what the average distance is from any point within the cluster to the center of the cluster. So that centroid that we found before, that were the same points we're using for the collinearity. We're trying to find the average distance between every point within the group to that center point. So here's our example asteroid again. Here's the clustering, and we see that here we have pretty, each of the points within the group are pretty close to the center. Here's our non-asteroid, and here's the clustering again for that image. And we see that the distance from all of these points to their centers is definitely a little bit greater than it was in the last example. So here's the actual values that our functions are going to return for the examples that we were just using, the asteroid and the non-asteroid. So first is the hue ratio. The asteroid has a very good hue ratio. It has all the colors that we're looking for in high proportion. The non-asteroid does not have these colors in as good proportion, so we're going to expect a high hue ratio to indicate an asteroid. Next feature is collinearity. A very low collinearity number is going to represent images moving in a linear fashion, whereas a higher collinearity number is going to, or collinearity metric, is going to represent an image that's not necessarily has a direction. And then the final one is the cluster distance, and here it's not so good for these images. It gets better for some of the other ones, but a low cluster distance means that the image is well grouped and not too spread out over the search space. Alright, so where's the AI here? Now that we've defined all of our features, we can move on to the neural net. So this type of classification is extremely well suited for building a neural network. We have a very clear set of training data. Basically, each possible output can be either affirmative, which is a 1, or a negative, which is a 0. And it's very easy to classify this by hand to use for the training data. And then each of the input features can be resolved to somewhere in a 0 to 1 range of metrics. So our hue value, our collinearity, and our distance values all fall within 0 to 1, which is good for our neural network. There's a small amount of input features which can really accurately define the item. So we only have 3 input features. We could have created a lot more. I actually tried creating a lot more, and it actually produces worse results. It's better to sort of narrow down the amount of features and make sure that they're very accurate in predicting whether an item is going to be positive or negative. And finally, this is great for neural network because the activation of a potential training piece of data on this network is going to be way faster than any other algorithm we could probably produce. It's going to be very fast, so we can do a lot of processing extremely quickly using this neural network once we have it trained. So building a neural network, I use PyBrains to do this. The resulting neural network, it's a supervised learning algorithm, obviously, because we have this training data and we're supervising it. I use a backpropagation trainer just because it's sort of a common way to do this, and it passes the errors back to the beginning. There's going to be 3 layers for our neural network. We're going to have an input layer, a single hidden layer, which will suffice for what we're doing, and an output layer, and we'll have 8 neurons. 3 input neurons to correspond to each of the 3 features that we defined, 4 hidden neurons, which represent the single hidden layer, and one output neuron, which is basically going to be 1 if it is a valid asteroid, and 0 if it is not a valid asteroid, or it's going to fall in some range close to 0 or close to 1. We give it a learning rate of 0.01 and a very high momentum of 0.99, and then we build a neural network. And this is what it ends up looking like with our 3 inputs, 4 hidden values, and 1 output value. And then we train the network. So we have, like I said, 250 valid items, 500 invalid items. We run our functions on each of those, and we say, for the 250 that they are a 1 for the output value is valid. For the 500, a 0 for the output value is valid. We train this for 5,000 iterations. This is sort of what took the longest, because sort of tweaking the previous values and running the iterations and checking the results takes a lot of time. For 5,000 iterations, this took about 3 hours. And we probably could have gotten by with less iterations, but we're getting better results with 5,000 iterations. So, and here are the results. So I ran 3 trials with separate data sets that were not part of the training data. For the first trial, I had 190 points. The neural network found 8 as being valid asteroids. Only 5 of them were actually valid, which gives us a pretty high false positive rate. In the second and third trials, though, this got a little bit better. We tried a total of 286 and 955 total individual images, and the false positives got a little bit better. And here's results for the false negatives, which is really the more important part. We want a really low false negative to make sure we're not throwing out valid asteroids, and this works really well for our data set. So we throw 190 images at it. We found all of the invalid images for the first one. The second one we found all but 1, and the last one we found about 1% as false negatives that were accidentally thrown away. So this is pretty good. In conclusion, I was able to do the neural network extremely quickly and process this data, and it's more accurate than the really quick and dirty algorithm that I had to use to get started. And then, because there's just simply so many, just in every image there's so many possible candidate asteroids, but also there's just so many images, this could be done really quickly, run over all the images to determine exactly where all the asteroids are. Really, the time-consuming part of this is spending time coming up with good features for the data. It's really important, because if the features aren't any good, the results are going to be really bad too. And then if we were to pair this with human validation, the process would become really quick and really accurate. So the dataset can run through a lot of images and produce pretty good results, and then the human can sit through and sort out the false positives or anything that sort of falls in the median between being a valid asteroid and not a valid asteroid. So just to wrap it up, I have a couple of references, mostly for the Sloan Digital Sky Survey, PyBrain, and a couple articles on the features I used, and that's about it. Thanks.
Piece of cake.